Okay. Okay. So basically you are given a MATLAB problem where we need to define a, or we can say simulate the heat distribution over a square plate. Okay, then we have the code here and I'll explain each step. So here we have the code and the graph. Okay, this code simulates the transient heat conduction in a two-dimensional square plate with a fixed. Here you can see with a fixed temperature boundary condition at the bottom of the plate, and you can see insulated boundaries on the side of the plate. Okay, now our goal is to observe how the temperature distribution evolves over time until it reaches a steady state condition at the end of the simulation time. So at first we have the parameters here that defines L equal 1.0, that is the length of the square plate, and x equal 20 and y equal 20. These are the set of special points in x and y direction respectively to 20. This means the plate will divide it into 20 into 20 size. Then we have alpha equal 0.01, which actually represents the thermal diffusivity of the material, shows how heat affects to the plate. Then we have the dx and dy, which actually calculate the special step in both x and y direction based on the length of the plate. Then we have the stability condition here. Okay, so this block checks if the Susan step dt is stable according to the CFL condition. If dt is too large, then it might raise an error. So here it is written in the comments that time step dt is too large for stability condition. Then we have here the initialized temperature field, where T initializes a matrix of 0 to represent the grid points, or you can say temperature at each point in the grid. Then we have the bottom row here where y equal to 0 actually, which is set to a fixed temperature of 100 degrees Celsius, simulating a heat source. Okay, then we have the time evolution step. Basically, t end here given as 1.0, which sets the total simulation time to 1 second. Then we have the num steps here. It shows how to calculate the total number of the time step size based on the total time and time step size. Okay, then we have this part over here, which shows they are written in the comments here that it's prepare for counterplating. Okay, so it shows, or you can say, basically this point over here, it it uh, um, it shows how a new figure is created for plotting. So basically a loop begins to iterate over the number of time steps. Inside the loop, a new temperature matrix T new is created to store the updated temperature for the next time step. Okay, then we have the updated temperature using FTCS method. Okay, that's the most important one basically here, over here. So here it is given actually two nested loops iterate over the internal points of the temperature matrix, excluding the boundaries. Okay, the temperature at each internal point ij is updated using the FTCS scheme, which calculates the new temperature based on the temperature of the neighboring points. Here The formula account for heat diffusion in both the x and y direction. Uh, then we apply insulated boundary condition as given in the question. It is the Newman boundary condition. The left and right sides, here you can see, this is the plate. The left and right sides of the plate are treated as left side, right side of the plate are treated as insulated, whereas the ground plate is at a steady condition, and the temperature gradient here is zero, since since both side of the wall are insulated. The temperature gradient is zero. Okay, then after writing the code here, we get such a graph over here, or you can say figure over here. It's a square plate. It has both side insulated. Ground ground plate at a degree of 100 degrees Celsius. You can see how time affects the plate. Okay. Okay. For instance, if we run this code, run this code. So we can see here that the problem draws a colorful map showing the temperature across the plate. You can see over here it's like yellow, blue, light blue. Here it is at the minimum temperature, and here it is at higher temperature. You can see. So hot areas might be yellow, cold areas might be blue, dark blue, whatever you want to say. Then this graph or this figure actually let us see how heat spreads from the bottom to the edge up through the plate as time goes on. So we can say this problem basically helps us to visualize how heat flows through a square metal plate when you heat it from the bottom while keeping the sides and top. So here the sides insulated. So it does by breaking the plate into a grid and calculating the temperature changes small step by small step. So here's the result. So a colorful map that changes over time. So thank you, and my name is Pranshul Alukdar, roll number MEB 22008.